This question requires that what will be the work done in moving a negative charge minus small q from point A to point B. So if there are two charges with equal charge but opposite polarities are separated with some distance, and point A and point B are all equal distances from the negative and the positive charge q's. So then what will be the amount of work done in moving the small q charges from point A to point B? So we know that the amount of work done is given by work done in electric field is the change in electric potential times the charge q. So before going to do the work done, we have to find the difference in electric potential between point A and point B. So then the potential at point A is given by directly potential at point A is equals to the potential due to the positive charges at point A and plus the potential of the negative q charges at point A, the sum of these two. So this is equals to potential at point A from due to the total potential at point A is given by k q positive divided by d plus k minus q divided by d. Then if we calculate this number, immediately we get that kq over d minus kq over d. Since the positive and the negative charges are equal but opposite in polarity, the potential at point A due to the two charges is equal to 0. Then the potential at point B is also potential at point B due to these two charges minus q and plus q is also calculated as the potential of the positive charge at point B plus the potential of the negative charges at point B. So this is equals to the potential at point B due to the positive charge is kq over d, since d is the distance from charge q to point B is d, and then plus k minus q divided by d. This is equals to kq over d minus kq over d. This is also 0. So from this, we can see that point A and the point B have the same potential. That means potential at B is equals to potential at A. This means that point A and point B are at equal potential, or they are equipotential points. So then the line which combines A and B, or line AB, is also equipotential line. So equipotential line is the line which combines all the points in an electric field at the same potential. So immediately we can see that the difference in electric potential between point A and B is given by potential at B minus potential at A, which is immediately 0. There is no difference in potential between two points at equal potential. So this means that we can see that work done is equals to change in electric potential times the negative charge q minus q, which is equals to 0, since the difference in potential is 0. So this indicates that the work done along the equipotential line is always 0, because electric field is perpendicular to the equipotential line always. That means if theta is 90 degree, force and the displacement are directly perpendicular to each other, work done is 0. So the correct answer is on alternative A. The work done in moving the negative charge from point A to point B is immediately 0, because line AB is equipotential line. So work done along the equipotential line is 0. An air-filled parallel plate capacitor with an initial capacitance of 1 picofarad has a plate separations of D, and it is air-filled, and the dielectric constants of the air is 1. Then at this time the capacitance is 1 picofarad. And secondly, the separation between the plate is doubled. That means D final become twice of D, and the wax is inserted between these two plates. That means to increase the capacitances of the capacitor. So if the wax is inserted and the distance between the two plates is doubled, then the final capacitances of the capacitor become 2 picofarad. And then what will be the dielectric constants, or the relative permittivities capacities of the waxes. So to find this, we use the concepts of a parallel plate capacitor. Capacitances of parallel plate capacitor is directly given by C is equals to the dielectric constant, permittivity of free space, area of the plate divided by the separation of the plates. But don't be confused here that kappa is the dielectric constant. But on some books, just we can see the term like epsilon r. Epsilon r means simply it is a relative permittivity, which we call the permittivity of material divided by the permittivity of free space, or it is called also the dielectric constant is here. But don't be confused. So keeping this in mind that the initial capacitance Ci is equals to the dielectric constants of air times permittivity of free space, area of the plates divided by the separation. And secondly, we know that after the wax is inserted in, the final capacitance become the permittivity, so dielectric constants of the wax times the permittivity of free space, area of the plates divided by the separation is here doubled, we have twice of the. So C initial is 1 picofarad, so 1 picofarad is equals to the dielectric constant of air is 1, so we can say simply epsilon naught A over T. And the final capacitance is 2 picofarad, which is equals to the dielectric constants of wax or kappa W, permittivity of free space A divided by twice of T. So to find the dielectric constants of the wax or kappa W, I can take the ratio of these two equations. That means 1 picofarad divided by 2 picofarad is equals to epsilon naught A over D divided by kappa W epsilon naught A divided by twice of D. And if you rearrange directly, we can see that epsilon naught A 2 times D divided by kappa W epsilon naught A times D. So we can cancel A with A, permittivity of free space with the permittivity of free space, and I can cancel D also with D. Here also picofarad cancel with picofarad. So finally we have left with 1 over 2 is equals to 2 over kappa W. So if you crisscross this equation and rearrange, finally kappa W or the dielectric constant of the wax become 4. So the correct answer is on alternative B. Electron is entered an electric field is of strength 5 times 10 raised to 3 Newton per Coulomb. And then what is the amount of force which is acting on this electron? So easily we can find that the electrostatic force on the charge moving in electric field is directly given by Q, magnitude of the charges times the strength of an electric field, or force is a vector and electric field is also a vector quantity. So then directly if we substitute in the equations, the values of Q is negative 1.6 times 10 raised to minus 19 Coulomb. This is the amount of charge of the electron multiplied with the strength of electric field, which is 5 times 10 raised to 5 Newton per Coulomb. So Coulomb cancel with a Coulomb, and 1.6 times 5 is, which is equals to minus 8 times 10 raised to, if we add this value, negative 19 plus 3 is minus 16 Newton is left. So the magnitude of the force on the electron in an electric field of this much strength is 8 times 10 raised to minus 16 Newton. So the correct answer is on alternative C. But here the negative sign indicates that the direction of the forces and electric fields are opposite to each other. This means that if the negative charge always enters electric field, it accelerates in opposite direction of the field. So the force on a negative charge in electric field is in opposite direction to the field itself. That means the negative charge always accelerate in the opposite direction of the field, and the positive charge always accelerate along the directions of the electric fields. Three capacitors C1, C2 and C3 are connected in series, and then the effective capacitances or the equivalent capacitance become 24/11 microfarad. Then C1 is 4 microfarad and C2 is 8 microfarad. And then what is the values of the C3 or the third capacitances to get these effective capacitances? To do this question directly, we use the series combination of capacitance. That means the total capacitance in series is equals to always given by 1 over C1 plus 1 over C2 plus 1 over C3. This is the series combinations of the capacitances. So in series combination, the effective capacitance or the total capacitances is less than the least capacitance in that circuit. So to decrease the effective capacitances, we have to connect the capacitor in series. To increase the effective capacitance, we have to connect the capacitors in parallel. So this is the one of the properties of combination of capacitors. So to do this directly, we can see that 1 over C total means simply, since C total is 24/11, 1 over C total is 11/24 microfarad. Then if I substitute this in formula, I can get that 1 over C total is 11/24 microfarad, which is equals to 1 over C1 is 4 microfarad plus 1 over C2 is 8 microfarad. And what will be the values of C3? We are going to find the values of this C3. So to find C3, just I can rearrange these equations. That means 1 over C3 is equals to, I transfer these numbers to this side, then I get that directly 11/24 microfarad minus 1/4 microfarad minus 1/8 microfarad. So I can use the LCM method, that is the least common multiple of 24, 4 and 8 is directly it is 24 microfarad. Then 24 microfarad divided by 24 microfarad is, I get 1 times 11 is 11 minus 24 microfarad divided by 4 is 6 times 1 is again 6. 24 microfarad divided by 8 is 3, and 3 times 1 is 3 itself is, so minus 3 directly. So this number become 11 minus 6 minus 3 is 2/24 microfarad is left. This is the values of 1/3. So if I take the reciprocal, C3 is equals to 24 microfarad over 2, or which is equals to 12 microfarads. So the correct answer is on alternative A. Okay, if 2-point charges Q1 and Q2 are separated, some distances are between them, then the force, electrostatic force between these two charges is initially, let me say F1, which is K times Q1, Q2 divided by R square. And then what is the values of the force F2 finally, if the distance between the charges is double. That means R2 become twice of R. So then the second force is F2 is equals to K Q1 Q2 divided by R2 square, which is equals to R2 square. This is equals to K Q1 Q2 divided by twice of r the whole square. So this is directly kq1 q2 divided by 4r square according to the Coulomb's laws of electrostatic force between the charges. So if I take the ratio of these two forces, so we can say F1 over F2 is equals to, since F1 is k q1 q2 divided by r square, which is the whole divided by k q1 q2 over 4r square. So if you rearrange this equation, you get directly k q1 q2 times 4r square divided by k q1 q2 r square. So k cancel with k, q1 cancel with q1, q2 cancel with q2, r square is cancelled with the r square. So we can get that the ratio of f1 and f2 become 4 over 1, or simply 4, and if we rearrange it, f2 is equals to f1 divided by 4. So if the distance between the charge is doubled, the force is reduced by the factor of 1 over 4, or F is reduced by 4. So the correct answer is on alternative C, which states that the force will be reduced by a factor of 1 over 4. That means F2 is 1 over 4 of F1. So to move a point charges of 2.5 times 10 raised to minus 6 Coulomb, or 2.5 micro Coulomb charge from point A to point B in electric field requires 6.3 times 10 raised to minus 4 joule of work. Then what is the electric potential differences between the points A and B in electric field? So we know that work done by electric force in electric field is, or work done in electric field is given by the difference in electric potential times the magnitude of the charge. Then from this equation directly we can see that delta V, or the potential difference, is work done divided by the magnitude of charge. So then the difference in potential is work done divided by the magnitude of charge, which is 6.3 times 10 raised to minus 4 joule divided by 2.5 times 10 raised to minus 6 Coulomb. So if you divide this number with this directly, you can get it is 2.52 times 10 raised to minus 4 plus 6 is directly, which is equals to 2 joule per Coulomb is volt. So the difference in electric potential between the 2 points in electric field is 2.52 times 10 raised to 2 volts. So the correct answer is on alternative B. Two positive point charges plus Q1 and plus Q2, or simply they are equal, separated by some distances 2d. Then we have 5 points here. Point A is exactly at the midpoints between the two charges, and point B is from the origin, it is twice of d. Point C is 3 times d, and point E is d to the right, and point D is also the distance d from the left. Then at what point is the electric field due to these two charges is minimum? So exactly, just we can say that the electric field between 2-point charge, when the polarity of the charges are the same, is only minimum at the point between the two charges. That means if the polarity of the charge is the same, we can get a zero electric field on the single points which is between the two charges. But outside the charges, or on the right and the left of the charges, we cannot get the minimum or zero electric fields if the polarity of the charges are the same. So we can say that the point which only exists between, or the midpoints of the charge 1 and 2 is point A. So we can say point A is the point at minimum electric fields due to the charge 1 and charge 2, or simply due to these two charges. So the correct answer is on alternative A, but we can prove this mathematically by doing the electric field strengths at each point, is point A, point B, point C, point D, and point E. We can do mathematically and prove it. This means that the electric field at point A is equal to the electric fields of charge Q1 plus the electric fields of charge Q2. So the sum of the electric field strengths at this point, point A, due to charge 1 and charge 2 is the electric field of charge 1 plus the electric field of charge 2. But at this point we can see that the electric field of charge 1 is toward the positive x-axis, that means along the direction of I, and the direction of electric field from the charge 2 is to the negative, that means electric field lines are always out from the positive charge. So if we have a positive charge, the direction of electric field lines are radially outward, so the fields are out from both charges. So then this is equals to the electric field due to charge 1 is simply Q1 divided by the distance between charge 1 and point A is simply d square, and the direction of this field is along the direction of I, plus Q2 over the distance between point A and charge 2 is also d, and but the direction is toward the left, so I write is minus I. So if you add these two, you can get that since the magnitude of Q1 and Q2 are equal, I can write KQ over d square I minus KQ over d square I. So this number immediately gives me 0. So the electric field at point A due to these two charges 0. So we can also prove for electric fields at point B. That means charge 2 is d distances from point B, and charge Q1 is at a point which is 3 times d. That means from here to point A is d distances, A to this point is also d, from E to B is also equal to d. So this means that point B is 3d from charge 1 and point B is d from charge 2. So then electric field at point B is equals to the electric field due to charge 1 plus the electric field due to charge 2. So electric field due to charge 1 is simply, we can write that Q1 divided by the distance between charge 1 and point B is, that is 3 times d the whole square, but its direction is still along I, and Q2 divided by d square, because the distance between point B and Q2 is d, still the direction is along the positive I. So we can add these two numbers directly since the magnitude of Q1 and Q2 are equal. KQ over 9d square plus KQ over d square. So along the direction of I, both of them, if we add these two numbers, then directly I can get that this is equals to 10KQ over 9d square along the direction of I, and so on and so forth. Just we can check also for electric field at point C and electric field at point D and check it for all of them. So the minimum value you get is at point A. So the electric field at point A is minimum due to the two charges. A parallel plate capacitor of capacitance is initially 10 microfarad. When the plate separation is simply D, Then we assume the capacitor is air filled, that means dielectric constant is assumed 1. Then what will be the new capacitance C2 of the capacitor if the separation of the plate is doubled? By keeping all other parameters the same or constants. So then we can see that by using the concepts of a parallel plate capacitor, the capacitance of a parallel plate capacitor C is given by C is equals to dielectric constant K or kappa, epsilon naught, the permittivity of free space, the area of the plate divided by the separation or D. So then initially C1 is equals to K epsilon naught A over D1. That means every other parameters are constant, not changed. Then this is equals to K epsilon naught A over simply D, because D1 is simply D. And secondly, the separation is doubled. That means C2 become kappa epsilon naught A over D2, which is equals to K epsilon naught A over twice of D, because separation is doubled. And then if I take the ratio, of these two numbers, C1 over C2, that means the first capacitance divided by the second capacitance is equals to K epsilon naught A over D times 2D over K epsilon naught times A. And if you rearrange directly, dielectric constant is cancelled, since every other parameters are constant except D is doubled. So I can cancel epsilon naught A with epsilon naught A, D with D, and we have left with 2. That means that C1 over C2 is equals to 2, means that I can find the values of C2. C2 is equals to C1 over 2. Since C1 is given, it is 10 microfarad. 10 microfarad divided by 2 is, which is 5 microfarad. So if the distance between the plate is doubled, then the capacitance of the capacitor become halved, or it is reduced by half. So the correct answer is on alternative B. So in the sketch below, which best describe the location of the negative charge or electrons when a negatively charged rod is brought near but not touching the conducting sphere. So if this is the conducting sphere and this is a negatively charged rod, so if we brought a negatively charged rod to a neutral sphere, that means simply we can see that if this is a negatively charged rod and this is the neutral sphere, then the positive charges are attracted toward this negative charge, toward this side, and the negative charges are repelled. So the correct diagram which indicates this phenomena is directly on B, on diagram B. But diagram B is on alternative D, which is the correct answer. So what is the electric potential of plus 5 Coulomb charges at a distance of 10 meters from that charge? The electric potential at any point P due to a point charge is given by V at any point is equals to KQ divided by R, which is equals to K times 5 Coulomb divided by R, which is 10 meters. But we know that K is 9 times 10 raised to 9 Newton meter square per Coulomb square. Then directly if we substitute the value, this is 9 times 10 raised to 9 times 5 Coulomb divided by 10 meter. So this is Newton meter square per Coulomb square. 1 Coulomb is cancelled by a Coulomb and 1 meter is cancelled by 1 meter, which is Newton meter per Coulomb, which is equals to, that is Joule per Coulomb, which is equals to 1 volt. Then if I divide this number, this by 5 is 2 and this by 5 is 1, 9 by 2 is 4.5. Directly we can get 4.5 times 10 raised to 9 volt is the electric potential of charge at 0.10 meter from the charges. So the correct answer is 4.5 times 10 raised to 9 volt. So the correct answer is on alternative C.